In this video, I want to present the Tri-state driver and explain some of the things that can be done with the Tri-state driver. Now, in a previous video, we explained the operation of the CMOS inverter shown at the left, and the symbol for this inverter is shown here. And we also talked about the CMOS switch, where this is the symbol for the CMOS switch. And we explained that the inverter takes whatever is at the input. If the input is at a high voltage, the NMOS transistor is on, the PMOS transistor is off, and we're at a low voltage. So it takes the input. If it's high, it makes the output low. If the input is low, the output is high. Now, the CMOS switch can exist in two different conditions. It can either be closed. When the switch is closed, both transistors are in the on condition. So the gate of the N channel is at a high voltage, and the gate of the P channel is at a low voltage. When the transistors are off and the switch is off, the gate of the P channel is at a high voltage, and the gate of the N channel is at a low voltage. So let's consider what we can do with this circuit. And let's consider how we can use this circuit to make a tri-state driver. Let's see what happens if we connect the output of the inverter over to the switch. So we're taking the output of this inverter, connecting it to the switch. And lo and behold, we get a tri-state driver. So let's explain what this circuit does. It's called tri-state. Tri means three. And this output node here has three different states. For example, let's say our CMOS switch is closed. Both the N channel and the P channel are in the on condition. In that case, the output will just take on whatever condition is at the output of the inverter. For example, if we have a high voltage here, we'll have a low voltage, and this low voltage will be transferred. So this output can exist in a low voltage state. Now, if we have a low voltage at the input to the inverter, we have a high voltage at the output, and the switch transfers the high voltage to this node. So the output can also be a high voltage. And there's a third state that the output can be in. Let's say that our switch is in the off condition. There's no conduction. So the output of the inverter is isolated from this node. And that is called the third state, or the high Z state. And it's also called the high impedance state. So the output can exist in three states. When the switch is in a closed position, the output is either high or low. When the switch is open, the output is disconnected, or said to be in the high Z, or the high impedance state. Now let's change this tri-state driver just a little bit. I'm going to erase part of the circuit here. Let's erase this connection. And I'm going to just set the brush here. I'm going to connect this point to here. The NMOS I'm going to connect over to here. So I have not changed the function or the operation of this tri-state driver at all. But let's make another small change. Let's remove this connection right here. at the output of the inverter. Now I've changed the circuit a little bit, but the function is still the same. Now I have a PMOS transistor here in series with another PMOS that connects to the output node. Here I have an N channel in series with another N channel that connects again to the output node. So this circuit is still a tri-state driver, but it's a little more compact. It takes up less area on the silicon chip. So let me redraw this new tri-state driver. This is our new tri-state driver circuit. It's the same as the old circuit, it's just drawn a little differently. So this is my P gate connection, my N gate connection. I have an N FET in series with another N FET and a P FET in series with another P FET. So same circuit, just drawn a little different. And here I'm introducing a new symbol for this new tri-state driver. So the symbol is like an inverter with the gate terminals, the P gate at the top and the N gate drawn at the bottom. Now let's consider again the operation. If our switch circuit is closed, if this transistor is on, which means its corresponding gate is at a low voltage, this N channel, if this gate is at a high voltage, this N FET is in the on condition. And that can be thought of as an inverter circuit with a small resistor in the drain and another small resistor forming the N channel to the N FET to ground, where the gate of this N FET goes to the gate of the P FET. So it forms the inverter function, but this P channel transistor is just a resistive device, and this N channel you can think of as a resistor. So the function is just like an inverter. However, again, if this PMOS transistor here is off and the NMOS is off, these resistors are open circuit and the output is detached from the circuit. So the output just floats there, or we call it the high Z state. It's completely disconnected from the circuit function. So let's consider what we can do with this tri-state driver. One thing I can do with this tri-state driver circuit is I can make a latch. Now a latch is a circuit that stores data. At the top I've shown a data signal, and I've plotted voltage in this axis versus time. And here my data is a 1, and at this time it can change or it may not change to a 0. Then at a later time it can change back to a 1, or it can stay at a 0. So the point is, this data can be either in a high state or a low state. And let's say that I want to generate a load pulse shown here. And this load pulse is going to sample the data at this time and store it into a latch. And a latch is a memory device that can use this data at a later time. So below I have two inverters connected to each other to form a memory element. So if my data at the input is low here, this inverter converts it to a high signal at the output. This inverter takes the high signal and it converts it to a low signal. So it is in a memory state. Again, if this is a high signal, the inverter makes this a low signal, and this becomes a high signal, and that data is remembered. So let me clean up this drawing just a little bit. I'm going to turn these two inverters into a latch circuit. So I'm going to take this inverter and I'm going to replace it with a tri-state driver. I'm going to take another tri-state driver and I'm going to connect it here. This is the gate of the P channel, and this is the gate of the N channel. And this I'm going to call Q, which is the output of my latch circuit. And this input to this tri-state driver is going to be my data signal. So that's the signal shown at the top. And now I need to generate a load signal to store data into this latch. So I'm going to use two inverters to make my load signals. So this output of the inverter will connect to the input of another inverter. I'm going to call this input my load signal. So when this load signal goes to a high voltage, as shown here at high voltage, I want to send data into this latch through this tri-state driver that's connected to the data source. So how can I do that? Well, I'm going to label this node. I'm going to give this a name. I'm going to call it NL for not load. I'm going to call this output. I'm going to label it L. And I'm going to connect L over to the NMOS of this input tri-state driver, and I'm going to connect the NL not load signal up here, and I'm going to reverse the connections on this upper tri-state driver. This is going to be the L signal, this will be the not L signal. So let's examine how this latch works. If this load pulse here becomes high, when this is at a high voltage, this is at a low voltage, this is at a high voltage, and this, since the NMOS is at a high voltage, the gate of the NMOS is a high voltage, this NL is low, the data will pass through this first tri-state driver and actually be inverted, and it will become not data at this node. Now this inverter here will take that data and it'll invert it back to data. Now when my load signal goes away, this will go to a low voltage, this will go to a high voltage, this will go to a low voltage, and that will enable this tri-state driver to transfer the data back to this point. So it'll take this data here, it'll invert it to not data, and the data will just be locked up in these two equivalent inverters. And at that time, the input tri-state driver becomes non-conducting. It is out of the picture. So the data, you can see how this latch works. When the load signal goes to a high voltage, this tri-state driver transfers the data into this latch circuit. Now when this load signal goes low, this tri-state driver goes from the detached condition to becoming like an inverter. and it reinforces the data. So again, the load signal, when the load signal is high, the data can come in here. This is out of the picture. And when the load signal goes low, this is out of the picture, and this one reinforces the data in our latch. So hopefully this gives you some idea of how the tri-state driver can act as a latch circuit. Now, I want to show you another neat thing I can do with this tri-state driver. I'm going to redraw the latch circuit below and show you another function that the tri-state driver can perform. Here I've redrawn the latch circuit, and I've also shown the symbol down below for the latch circuit. Now I want to show you what I can do by changing one connection in this latch circuit. I'm going to remove this part of the circuit. And now I have an entirely different circuit just by removing that one connection. And this circuit is called a MUX, or a multiplexer. And I want to change a few more. I want to change the names. So let's get rid of this name, the data input. And let's remove our symbol for now, since it's no longer a latch circuit. And I'm going to change the name of this signal, and the Q, I'm going to change the name. But it's basically, you can see it's the same circuit. Let me enable my brush. Now I'm going to change the name of this input to A. It was data, we'll call it A. In our new circuit, this input will be called B. And this will be called out, O-U-T. This input that was my load signal, I'm going to call it S-A, which means select A. So when SA is high, I'm going to select the A input. The B input will be cut off because the B input tri-state driver will be in the high Z mode. And the A will become inverted at this node and then turn back to A at this node. So the A signal will be transferred to the out node if the SA signal is high, or the select A is high. But if the select A signal is in a low voltage condition, this is low voltage, high voltage, low voltage. So in this situation, this tri-state driver passes the data from B to the output. And this tri-state driver is out of the picture. So again, to summarize, if select A is high, the data comes through this path to the output. If select A is low, my data source is here to the output. And this circuit is called a MUX, or a multiplexer. And let's sketch the symbol for a multiplexer. So the multiplexer has two inputs, A input and a B input. It has an output, and it has a select signal. Let's select A. So again, if select A is at high condition, the A signal, whatever is at this node, is transferred to the output. If select A is in a low state, it sends the B signal sends this node over to the output. So this gives you some idea of the different circuits that we can do. Just starting with an inverter and a CMOS switch, we can turn that into a tri-state driver. And we can take the tri-state driver and an inverter and we can create a latch circuit to store data. And then just making a very simple change to that latch circuit. By removing one connection, we can turn that circuit into a MUX or a multiplexer.